Okay, isang magandang hapon? Hapon po ulit sa inyo. Halatang kapapangan eh, walang age eh. But yeah, hello, magandang hapon po sa inyong lahat. And welcome to our last Spotlight Talk for this year's World Quantum Week celebration here in the Philippines. Woo! Okay, so nice meeting you for those that first time that are here. Although we're just a handful on the call, but sa mga nanonood ng recording natin, hello, hello. Hope that you are able to catch up on our sessions for a while. And yeah, I think mayroong mga nag-join kanina sa quiz bit. Ayan, so hopefully nag-enjoy kayo. Hindi ako nakarinig pa ng chika. So baka mamaya after yung session na 'to ay makakarinig ako ng chika sa mga ano natin. But if na-miss niyo yung quiz bit, you can definitely join yung susunod this 3 PM. So after ng talk na 'to, now we will have another competition, in a bit, for Quantum Circuit Crunch naman, 'no? And yeah, okay, so for now, let's go through our last spotlight talk for today. So this one is very special as well, no? But yeah, before doing that, let me ask, how are you today? Ayan, kaya pa ba? Grabe, kaya pa ba? So you can type one on the chat if you're just chilling on the weekend. Sana all, no? Number two, if you just want to sleep, ayan, antok na antok. Ako medyo two ako eh, feel ko. And number three, if you just want quantum, 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 or three, number four, hoo last spot, like, talk about, ooh. Kaming mga organizers, medyo nasa foreign kami kasi, like, of course, organizing this, on top of being a student, di ba? But, yeah, ayan, may nakikita ko sa chat, number two, inaantok. Number four, last spotlight talk na. May number one, that's just chilling. Okay, just chilling. Ano number if nervous? Siguro ano, superposition ng naka-superposition ka. So, it's a valid state of its own kasi naka-superposition. 'Di ba? 2, 3, and 4, ayan, ano ba yan? Baka ano yan, linear ano lang yan. Kasi hindi siya kakit. Eh, napaka-nerdy. And then, but yeah, thank you guys. I know na very familiar yung mga names nyo. Nakikita ko kayo lagi sa mga sessions natin. Okay, great. So yeah, welcome again to our Spotlight Talk number 11. So this one is very special since this one is parang we might be able to relate to this person more since katulad mo, I would assume na most of us here are students, no? And yeah, let me introduce to you our speaker for this session, si Paulo Miguel F. Soria. He is a fourth year BS Applied Physics student from University of San Carlos, and he's specializing in quantum computing, particularly in quantum state discrimination. So I'm sure he will tell us more about that. And he is a member on the newly opened Quantum AI Nexus Innovation Hub in the University of San Carlos. So if you don't know, Canix or tama ba, Canix or Canix, that's one of the first labs in the Philippines na nagkaroon ng quantum computer and not um, a nuclear magnetic resonance, yung spin Q na na quantum computer, no, for research and education. So he might be one of the first in the Philippines. I'm not sure. Probably not, but probably one of the leading doing research. Imagine you're doing research on a actual quantum computer na hindi lang siya sa cloud access. But yeah, I mean I mean I'll let him introduce himself further. So let's give a virtual round of applause to Paolo.
Okay. Uh, am I sharing the right screen?
Yep, yep, we can see your, yeah,
Okay.
screen, the NMR, yeah. So,
All right. Hello, everyone. Good afternoon. My name is Paulo Miguel Soria, and again, thank you for the introduction. Uh, I'll be talking about the SpinQ NMR Gemini quantum computer, but mostly about my experience using using this quantum computer rather than the hardware. I mean, I will talk about the hardware just a little bit because like the cap past couple of talks, especially from Dr. Fritz Diorico. He talked about the hardwares of quantum computing already, and I don't want to like make it redundant. But yeah, this is the SpinQ NMR Gemini quantum computer. I was also tasked to like showcase Connix, but since the it's still under construction, so I'll just talk about my experience using the quantum computer for my research instead. So a little bit about me. I'm a fourth year applied physics major from University of San Carlos. I was an okay, disclaimer here before everything else. I was an ABM student, and transition was a struggle. So just like I have seen a couple of students attend our lectures the past week, so I wanted to like put that there to have like a little relative what relatability. Yeah, relatability. Kasi some students also uh, didn't really get any background in physics or anything related to it. So I'm just putting that in as a as something to like think about. Yeah. And for my thesis, I'm specializing on quantum state discrimination. This right here is a photo of me with the quantum computer when it was first announced in University of San Carlos. This was the opening of Conics, and also added this little book called the Quantum Mechanics. It's a crash course for quantum mechanics, and it's a funny story. There's a funny story behind this. I wanted to share. Back then when I was in high school, I was a uh, nerd. I wanted to study physics, but my parents were pushing me to like study accountancy. That's why I, I studied ABM instead of STEM. So I studied like physics as just a hobby. It's just a hobby. But one of my friends, my old time friends, uh, thought I was like really really interested in physics and gave me this book. So I gladly took it, received it. But when I opened it, I did not understand a single thing. It was like the math was so complex that I was also in high school, but the mathematics was so complex that I could not understand any of it. But I still kept it because it's one of my uh, keepsakes. As someone who believed. And now that I'm in physics, fourth year physics, I can finally understand, which was such a relief. I can finally understand the book, can finally make use of the book, and every now and then I take a look at the book and get reminded of how nature versus nurture. With the right nurture, you can get to wherever you want. But yeah, let's go ahead with the hardware, I guess, with the quantum computer. Again, I mentioned that I won't be like talking much about this, so we'll just skim through this. This is the hardware setup of the quantum computer. Also, uh, this one again, the quantum computer. It doesn't look like much. It looks like a printer. Even a lot of people have said it looks like a printer, and that's because it's a portable quantum computer. It doesn't really require massive cooling like with those from IBM or Google. And inside, this is what it looks like, right? So um, inside it uses nuclear magnetic resonance and as a spin instead of superconducting coils. And inside as well there's only 2 qubits. So with the radio frequency, it delivers controlled pulse sequences to nuclear spins. That way we can have 2 qubits here, and instead of superconducting coils, again using nuclear magnetic resonance to create spin and use that for calculations. And one great thing about this photo is also taken from KissCon last year. I wanted to attend, but I was unfortunately I didn't get to register in time, so I was only there in spirit, online. But the cool thing about this quantum computer is it's cool. Literally, it doesn't really require like massive cooling. It only requires it can operate under room temperature. because again, it doesn't use the superconducting coils, so you can just like take this wherever you want and start fiddling with it, and it's pretty cool, literally. And then let's talk about what the quantum computer is like, really. The spin q nuclear magnetic resonance quantum computer. Again, this is just a 2 qubit quantum computer, so it's not all powerful, right? And it's based on nuclear magnetic resonance, as I mentioned. Now, inside, once you open up the quantum computer, after calibrating, you will be met with this screen on the bottom left. So you can see here real quantum computing, quantum course exercise, quantum game. Personally, I haven't tried the quantum game because it doesn't load for me for some reason. But there is quantum chess there, where it's like playing chess, but it's instead of playing chess, you can like put your pieces into a superposition, and it's pretty fun. But I haven't tried it on the hardware. I've tried it online, but yeah. um and once you click on the quantum course, you can see a bunch of lectures here for introduction. You'll be taught about qubits, or like bits, the difference between bits and qubits. um uh, a lecture on quantum computing circuit model, the like different algorithms here, the Dutch algorithm, and even like mathematical background to understand quantum computing. And then you can even like have a lecture on making a quantum computer even. Um, but the real kicker here is our real quantum computing, because you know this device isn't just for educational purposes, it's also for experimentation, and we can do that with our real quantum computing. So let me just read through the key features to qubit NMR quantum computer. I mentioned that earlier, and designed for education and experimentation. Now, let's talk about bits and qubits. I'm pretty sure you guys are familiar with qubits already, but with classical bits, it can only be 0 or 1. But with a qubit, you can put it in a state of superposition where it's both 1 and 0 at the same time. So, since this is a 2 qubit quantum computer, we can represent four possible states, with each qubit having two states, and more importantly, we can explore like interference or a superposition with this, or entanglement with this, with having 2 qubits. And then, okay, so uh, I guess I want to talk about the capabilities of the quantum computer and the limitations of the quantum computer before everything else. As having a quantum computer here in the Philippines, a lot of people actually have been asked a lot whether or not this quantum computer can be is capable of running this, capable of running that, and all that. So I thought I'd give like a little clarification first. But with 2 qubits, it's capable of running all basic quantum gates, right? So as you can see here on the left photo, we have a bunch of gates: the Hadamard gate, identity gate, poly X, poly Y, poly Z, even the C naught gate, where you could entangle one qubit to the other. You can do that with this quantum computer. You can also demonstrate core quantum concepts, such as superposition and entanglement. And of course, you can also run simplified famous algorithms. This algorithm here I am showing you is the Dutch algorithm. It's a sample algorithm that you can find in the software itself. And of course, you can also perform real quantum experiments, which is what I'm doing with my thesis right here on the bottom right. Now, the thing though, limitations, because it's only a 2 qubit quantum computer, it's not all powerful, right? It cannot. One of the frequent questions I've been asked is if it can, break encryption, or like uh, do decrypt. But unfortunately, no, it cannot. It cannot also, solve real world problems, like like large scale real world problems at least. And because it's only 2 qubits. It's only 2 qubits. It cannot compete with supercomputers. I don't even know if it can like compete with like high end classical computers even. But yeah, I just like wanted to put that out there because yeah, a lot of questions about that. But everything else I am studying for my thesis. That way, things can be improved, like like in the theory side. Everything can be improved. And speaking of thesis, oh wait, here my workflow. So what I would do with the quantum computer, what I would do with the quantum computer is first of all design quantum circuits. So we have a bunch of photos here of circuits. I did not design all of them. This top left here is the Bell inequality. I did not design that. I just grabbed it off the internet. And I would simulate it. I would simulate the results and run it on the hardware. Actually, it's quite easy. Simulating and running it on the hardware is the easier part because if you can see here on the right photos, we have 2 bars, right? Uh, this is for each state, so there are 4 states because I'm using 2 qubits and 2 bars. One for the real result, the real calculated result from the quantum computer, and one simulated result from like a theoretical result. So yeah, that's basically what I do. I'll try and design like quantum circuits, simulate and run it on the hardware, and then compare the theoretical results versus the real results that we're getting. And um, I just want to like uh, remind everyone that simulation is different from reality. In simulation, everything is perfect, but of course, on real hardware, we can see like imperfections and deviations, partly because of noise and decoherence mainly. And this is actually one of the bigger challenges with quantum computing. You can see here that in one photo, our real result is 0.45, while our simulated result is just 0.42. Although in our right photo, our real result and simulated result coincide at 100%. And in the middle photo, real result is 0.05 and simulated is 0.06. These are, by the way, probabilities. So if you're wondering what these numbers represent, these are probabilities. As someone famous said, quantum mechanics plays on probabilities, and uh, sometimes you're not. I mean, like most of the time, you're not gonna see like a perfect real result uh, compared to like simulated result because it's there are a lot of factors, decoherence, superposition fades when you put a qubit into superposition, eventually it'll fade. The thing with the quantum computer is when you run, it does take a while. I mean, it's not like that long, but it takes like a minute or two for the quantum computer to calculate what you're running in your circuit. So as the process goes on, superposition might fade over time. Uh, Also, phases might get randomized. Rotation on the z, the phase, it might get randomized over time, or like uh, potentially entanglement weakens, which is thing I've been studying as well with my thesis. And it could also be from the T1 and T2 relaxation times, and the what's T2 again, dephasing, right? So it could also be from that. And again, uh, uh, this the quantum computer, I've only used the quantum computer like for like a month or so for my thesis. I haven't really like uh, fully understood it yet. I've been making research, working overtime at the lab to complete my thesis, and one of the parts of my thesis are the reason why uh, we're not getting the real. We're not. approaching the simulated result with our real result, and it could be with the decoherence or the noise. And speaking of thesis, my thesis is centered around quantum state discrimination. It's basically um, it's basically distinguishing two very very similar signals, right? So my research focus is distinguishing quantum states with optimal accuracy. Optimal accuracy is it's a loose term because like it's it's two very very similar quantum states, and of course the more similar you go with like each quantum state, the higher your probability for error is, because uh, there might be a chance that you'll get it wrong. And what I'm trying to find out is the optimal accuracy for distinguishing quantum states with the hardware itself, right? We have theories for that now, Hellstrom bound theory, uh, Fisher quantum information, that could help with the theoretical aspect, but I'm focused on the hardware. And yeah, hardware characterization and benchmarking by comparing results to theoretical value, as I mentioned earlier. Now, the challenges here again are the noise interference, the coherence, overlapping quantum states. The smaller the angle goes, or like the more similar it goes from one quantum state to another. Uh, of course, it'll overlap, and it'll be more and more difficult to distinguish one from the other. And of course our fundamental measurement limits, which is based on the Hellstrom bound theorem and the Fisher quantum information. Now, you can see here like there's a block sphere. I added like a block sphere. I should have drawn it myself, really, but essentially what my thesis is trying to achieve here, right? So imagine we have like psi 1 here and psi 2. It's kind of far apart, but imagine they were like really close. Okay, so they're far apart now. Let's just think of it that way. They're far apart now, so it's easy to distinguish one from the other, right? From this psi 1 from psi 2, because they're far apart. So think of like psi 1 as our noise here, our noise, and psi 2 as our signal. That way, it's so much easier to distinguish a real signal and apart from our noise, our psi 1, because they're far apart. But imagine they were like very very close, like psi 2 is like really next to a psi 1, right? That would make it almost impossible for for us to like distinguish real noise. I mean, a real signal versus the noise, right? But that's really the goal of the thesis here, to distinguish, to discriminate like quantum states at its like lowest possible level, to also test the hardware. Now, what this helps with is potentially, if we could get to develop this with the right hardware, it could potentially help with telecommunications. You know, Eh, I know even though the system is like kind of small. Wait, hang on. Even though the oops, even though the system is small, the concepts apply to like large scale practices, right? So in telecommunications, we could potentially uh, use this the information gathered here, quantum state discrimination, to detect weak or overlapping signals, or at least until Hellstrom bound kicks in, again, like the measurement limit. So if we get to implement this the quantum state discrimination with telecommunications or signals, we could potentially have more accurate decoding as well of transmitted information. We could also have lower error rates in noisy channels, and this could potentially be a foundation to quantum cryptography. Quantum cryptography, yeah. Yesterday, was it, or last Friday, there was a speaker, I think Miss Kylie. I forgot how like her name is supposed to be pronounced. She was talking about uh, passing information through quantum teleportation, and it could also relate to that. It could also be used for deep space probes. So in deep space communication, signals are so weak that we're limited by quantum effects. Um, with quantum state discrimination, it could help us extract as much information from as little signal as possible. It could the key benefits here would be precise detection of weak quantum signals over vast distances. Of course, with deep space, we are dealing with vast distances with very very weak signals. I don't know if like it's that weak of a signal, but with as distance increases, uh, I would imagine the signal would weaken as well. And of course, we could use this. We could use quantum state discrimination as an improved error correction for interplanetary transmissions. We could also use it to improve quantum enhanced sensing for space exploration, and potentially a better way of detecting exoplanets. During my proposal, I talked about like a way to detect exoplanets using quantum state discrimination. Um, Actually, in hindsight, I should have added that in this presentation. But yeah, potentially it could be a way of detecting exoplanets. If you guys were aware, during the recent Artemis mission, there was a loss of signal because they went to the far side of the moon. And maybe I don't want to like overclaim, but maybe improvements with quantum state discrimination could help uh, with like especially with space exploration where signal gets really really weak. And it could also be helpful for medical imaging. you know uh, we often like use signals in medical scans, and it's helpful to distinguish similar looking signals. And quantum state discrimination provides a framework for making that optimal decision making. And in this like particular field though, it's more theoretical more so than like practical, because like medical imaging it's pretty good now. uh, but the potential key benefits here would be the detection of subtle differences in signals, as I mentioned, better resolution in imaging systems, and improved sensitivity in diagnostics. There's a photo here of the MRI, which we could potentially improve with quantum state discrimination, because there might be signals that are too similar, that could be broken down into more specific information with quantum state discrimination. And what does that mean for the future of quantum computing technology here in the Philippines? Last night, Mr. Sean's talked about talk talked about the discrepancy of the Filipino education, or like the Filipino scientific literacy compared to other countries. And he's lucky enough and privileged enough to be able to like experience uh, uh, what it's like studying abroad. And he mentioned that we really are lacking not just in funds but also in education. But with this uh this is still the first. I mean, the spin q nmr quantum computer is still, I don't know if it's the first university acquired. I mean, I know QCSP has a quantum computer, right? You guys went to what was that school in Cebu where you had like high school students, you demoed to high school students. But essentially, uh as more schools, more institutions, more universities procure this quantum computer, we could potentially uh, accelerate our quantum information literacy here in the Philippines. You know, because access to quantum systems, even small, is rare in the Philippines. As uh, you know, most of us researchers would have to like rely on cloud-based quantum computing services, and with this, you know, we'd be able to really have our hands-on practice with quantum computing. And you know, it's not, again, it's not just experimentation with this quantum computer. We could also use it for education because there are multiple courses that is integrated into the hardware, into the quantum computer itself. And it also allows learners to move from theory to experimentation, because you know, uh, it also ties with the whole uh, we'd be able to use it uh, face to face instead of just cloud. You know, we're going from we're just learning quantum computing or quantum physics in theory to actual hands-on experimentation, and also help build local expertise early. um, we might not be able to like we're not like, of course we're not leading, right? But with this, we'd be able to shorten the gap. At least we'd be able to catch up to countries that are leading with quantum technology, quantum computing uh, sciences. And you know, that way, once quantum computing does become prevalent, does become more dominant in the field, though I don't know when yet. You know, Filipinos will not fall behind. Uh, will at least be able to like catch up to the rest of the world, really. But yeah, that's basically it. That's all for my presentation. It's all just you know, my experience with the quantum computer, and what the quantum computer could do for the Philippines.
Great,
Oops. Okay.
awesome. Yeah, and very interesting from the perspective that we can actually relate to. So maybe baka pwede niyo kausapin yung inyong mga admin sa school. Hindi, joke lang. Pwede po bumili po ng ano, ng quantum computer. And then, but yeah, it's a great thing. It's a great start, I would say. Na yeah, at least we're not starting from scratch, and at least we can like what is it like na parang kasi parang kapag mag-run ka on the cloud, 'di ba, na parang it's really abstracted na parang nangyari ba talaga yung experiment to? Pero pa
Yeah,
what isa yun ba like when you press the buttons, how do you feel na parang oh nag-run yun sa harap ko, parang ganun.
I think like the best part, well, like, oh, to like explain na I can really tell that it's running, is the whirring of like the machine. That's like with I tried the cloud services as well during the first semester. We University of San Carlos didn't have the quantum computer yet, so you know, as a way for me to like test out the theories, I had to like rely on cloud services, see if like I could get the results I wanted. But aside from it taking way too long, especially like at night, because like the queue is like super long, uh, it feels like it doesn't feel like real. Like it doesn't feel as good maybe as like handling the quantum computer yourself. It's like you build circuits online, right? And then like you submit it, and then like wait a couple of hours to get the results, and then afterwards, that's that. But with the quantum computer, you can feel it whirring, you can hear the noise. And it's you can actually, yeah, tell that, you know, it's real, it's right in front of you.
Right. Also, meron ko bang intrusive thoughts na buksan yung quantum computer?
I
Like, okay
tried, I
naman sa
tried.
loob.
Gusto ko
Yeah.
ngang buksan, pero di ko alam kasi I don't wanna like fiddle with it. It's a 1.2 million quantum computer. I don't have the money to replace that. Yun nga yung pressure. It's like the pressure is so high because I'm the first. to ever use it in the whole University of San Carlos. And professors, students even would tell me, you have to be careful. Because if you break that, that's 1.2 million pesos out of your pocket. I don't have that kind of money.
Very awesome. Like I think I'm sure it's more than the words that you're saying right now. Your kind of experience. So yeah, guys, if you have questions, you can drop them in the chat. No, so I can answer them. And yeah, just curious. When you started your thesis, parang wala pang quantum computer nun, wala pang spin
Mm.
cube. So were you planning to do it all? I mean, I guess you have no choice, but to do it all online, no? Tapos how paano anong nangyari? Like, nung dumating na siya, did you change your plans? Gano'n. Parang, yeah.
Uh,
Maybe,
well, there was a change of plans. Ano kasi, last semester, I was going to like make a thesis on ionosones sa QNSS. Tapos, middle of the semester, Dr. Roland Otadoy told me na the quantum computer, the thing kasi is, wala pa akong proper foundation with my thesis like in the middle of the semester, which, is bad. It's really bad. So, during the middle of the semester, uh, I there was also like lots of earthquakes here in Cebu, Baguio, and all that. So I really wasn't able to like uh, move forward with my thesis. Timing nun, kasi during that week, uh, my thesis advisor, Dr. Roland Otadoy, told me that the quantum computer will be arriving soon. So I should, if I want to be the first to ever use the quantum computer in not just in USC but like potentially the Philippines at that time, for my thesis, for a thesis, I could shift my thesis towards quantum computing. So that's what I did. So like the rest of the first semester, I was mostly focused on just theory, just theory lang talaga kasi uh, wala pang hardware nun. So it was really difficult, and I could only rely on the cloud computing. Tapos, the thing then, when the computer arrived na, and it was available for me to use, it was just last March. So just last month, actually February. Oh no, March, yeah, early March. So recent lang talaga na na naka I'm like having a hands-on experience with the quantum computer itself. And that's when I realized my initial thesis was on just single qubits, quantum state discrimination with single qubits. And then I realized that I could do so much better with entangling qubits, right? So that's why I did. I changed my thesis. It's now entanglement enhanced quantum state discrimination. I had to like talk to my advisor about that, and then rewrite most of my manuscript. But yeah, there's a lot of adjustments. A lot of adjustments.
awesome. Great. So while we're on the topic of your thesis, balikan na lang natin yung question ni Sir Vincent later. So Pao,
Okay.
how far are you along now with your thesis? Is your data starting to show up?
that's a funny. That's a funny question because with my thesis, it's also uh what I okay, I'll answer this first, and then like with my thesis, I'm still gathering data as much as possible. Um, right now, I've hit a rock with quantum limitations. Uh, so far, right now, what I'm doing kasi is, you know, uh, with the block sphere, I'm like doing 2 qubits now. So I'm rotating 1 qubit like a specific uh degree on the block sphere. So right now I'm hitting a wall with like the minimum amount of rotation. So I could definitely have it improved within the next couple of weeks. But right now, it's just like the data gathering is still like probably halfway. Tapos yung defense naman is next month now, so it's a funny question. I think I'm cooked, but I think I can also do this if I if I just like work more overtime in the laboratory.
Great. Bitbitin mo na lang kaya, parang toaster lang naman siya, eh, parang puwede mo ilagay sa bag, eh.
It's
Oo,
really heavy though. It's really heavy.
oh, yeah. Okay, may question si Vincent. Can you differentiate in simplest terms the quantum state discrimination from quantum teleportation, maybe for someone like us that doesn't have the physics background? Yeah.
Mm. Okay. I don't like specifically know talaga the quantum teleportation as deep as Miss Kaylee, who we had talked about it last Friday, right? But uh, with with quantum state discrimination, kasi it's basically just discriminate. You're not actually like teleporting any information. All you're doing is basically differentiating uh, two signals. So let's say in like the simplest term siguro na I can come up with is like listening to a whisper in a rain. Parang ganun. Kasi, with quantum state discrimination, it's high overlap, high noise with a small signal. That's what I'm like trying to study with my thesis. So it's not like I'm teleporting information or like with superposition. Kasi with superposition you can technically teleport information, as you if you know this the information of this, if these two uh, qubits are entangled, right? Once you know the information for this, you'll immediately know the information for this. But it doesn't really translate like equally from quantum teleportation to quantum state discrimination, because really all I'm doing with quantum state discrimination again is just finding the real signal uh amidst like loud noise. That's it. Yeah.
Awesome, great. Just curious about the computer kasi kapag when you're talking about quantum computers, we're usually talking about the specs, 'di ba? Okay, so it's
Mm.
two qubits. And then how many operations can you usually like apply? Kasi yung decoherence time, parang how many gates can you apply on the computer right now?
Mm, yeah. Yun din yung I also tested that like before, because I was curious about like how far I can go with like my gates, right? Before decoherence really destroys my data. That's the question, right? But the thing is, I haven't really like explored that much yet, because right now the furthest I've done is it's still related to my thesis, but instead of like so I put like uh I guess instead of like, so one qubit zero, right? I put it in a superposition state, and then I entangled it three times with qubit one, and then I rotated qubit one a certain degree for like to simulate the signal, and then I entangled it three more times back to qubit zero, and before undoing the superposition. And so far, wala namang massive na decoherence effect, with despite going through six total superposition, entanglements. Maybe I can probably like write about something like the limits of the quantum gates, or like maybe like specifically on entanglement, or maybe sa superposition that would affect decoherence. But so far, even with like 10 gates, it doesn't really affect the signal or like the results that much.
Great. And I'm also curious naman, like how much leeway can you do in terms of programming? Like, is it just the gates, naka-prepare na ba sila on the quantum computer, tas i-drop mo na lang and the degree for rotation gates? Or do you have the flexibility on actually like shaping the pulses na ipopulse dun sa mga qubits?
Ah, actually, yun din yung like worry ko. Because like before the first semester, I really studied the Qiskit na Qiskit na what's that called? Like extension for
Mhm.
Python, because I thought I'd be having to like code everything to through Python. But with a quantum computer, it's actually so much easier because all you have to do is there are already gates up top, right? All you have to do is drag them down, and there are also gates that you can uh, specific gates that allows for specific measurements. So like a rotation on like this axis, a rotation on that axis, and to a specific certain degree, or even like the square root of 90 of like this axis.
Yeah, that's interesting. And from the chat, Mr. Bobby, you would need API for the spin queue to, I guess I would assume yung tinatanong ko if you can like really shape the pulses into the qubits. You can upgrade to Gemini Mini so you can use Python to connect to spin queue. Interesting. Okay. May question ulit si Sir Shift. How sensitive is the quantum computer towards outside magnetic fields?
Oh, right. The quantum computer actually has like the in part of the documentation of the quantum computer, it advises at least zero point 0.3 meters away, like, so keep your electronics away zero point 0.3 meters away from like the quantum computer itself, because it the ma- like the quantum computer runs on nuclear magnetic resonance, right? So the magnetic field of I mean, I'm pretty sure there is like a what is that called, like
Shielding?
shroud of like a magnetic field na shroud. I forgot, that's in UP2 or like EMAG class namin. I forgot the term. uh well, there should be like an electromagnetic shroud over it, but just to be safe, uh at least zero point 0.3 meters away, at least zero point 0.3 meters away from the quantum computer would be the safest, because otherwise you'd run the risk of your data getting corrupted, or not corrupted, messing up with your data because of like the magnetic fields uh clashing against the devices that are nearby. And yeah, that's basically
Great.
it.
Interesting. So parang you would need to like rearrange the room na
Yeah,
parang
yeah.
hindi pwedeng may laptop tas katabi yung ano, no? Yeah.
Sa
Okay.
lab nga, I have to like remind like the people in our lab to like keep their electronics away whenever I'm like running. I'd even like remove my watch, take off uh like every ano, there's like everything that has magnets on me before I operate the quantum computer, because I mean zero point 0.3 meters, it's you can have like that's like a decent uh leverage, but you can never be too safe. So I have to like remind everyone to like keep their phones away, keep their laptops away. I have to like take off my watch and all that.
Yeah. I mean, it's definitely much easier to do that kesa sa mag cryogenics ka ba, right?
Oo nga.
Like to wear PPE and such. So
Yeah,
yeah. Interesting. So, practical experience that you've shared. So, I think that ends our Q&A. Thank you so much, Pao, for that very very wonderful talk.
thank you.
And thank you for also sharing your hope to have this around the Philippines as well. So again, gusto pong magkaroon ng quantum computer, just let us know. I can connect you with the supplier. Kung hindi mo nakukuha itong computer sa bahay, we have that disposable income, why not, 'di ba? But yeah, thank you so much again, Pau, and thank you so much po sa inyong lahat sa pag-a-attend ng ating session for today. Yes, definitely very first student researcher for the quantum computer. And yeah, hopefully not the last one. Yeah, great. I think we can conclude our session for this portion. Again, thank you so much, Pau. We can take a photo. So if you can turn on your cameras, so that we can take a photo with Pau. If you can't, pwede naman na heart react so we can see your presence kahit na virtual presence. Hi, Mark. Ayan. Parang presko dyan. Oo, ang init sa Pilipinas ngayon, no? Okay. Hello, hi po, Sir Bobby. Okay, great. So I'll take the photo now. Okay, heart reacts lang. One, two, three, smile. All right. And once more. One, two, three. Ayan, si Razel Mamabal. One, two, three, smile. Awesome. Okay. Thank you so much po for everyone.
Thank
Um,
you.
Thank you again, Pao. Our next session po is now, right, in 4 minutes. Punta po ulit tayo sa platform, or www.qcsc.ph. Meron po tayong competition, Quantum Circuit Crunch, that will be happening in a few minutes. So if you want to join, just register doon, like right now, kasi need nyo nang mag-register doon. No, but if not, okay lang, we can, ako rin, mag-join ako just to watch our competitors to try and create the quantum circuits. And then after po nun, I think we will end at 4 p.m. nun. We will have an hour of a break. And then 5 p.m. po ulit dito sa Zoom meeting na to. I mean, nasa platform naman lahat. But we will have our culminating event just to end the whole World Quantum Week celebration po natin. Okay? So again, lipat na lang po tayo sa Zoom if you want to watch the Quantum Circuit Crunch, and then see you at 5 p.m. Here on Zoom para sa ating culminating talk. Again, maraming maraming salamat po and see you in a bit. Bye-bye. I'll just end the call for everyone.